During lockdown, we had all our classes online, which made it very difficult to focus, especially with physics, because it's so easy to get stuck in a loop of questions and go off on way too many tangents. I mean, the open new tab button is always right there. So how many times would you have to slap a chicken to cook it? Alright, is everyone done with those 11 exercises? Oh shoot, I forgot I'm in class. So one of the topics we were doing during that was particles, which is very fun. And during that, my teacher, who we're going to call Brian,
it's Professor Brian Cox,
talked about how protons are the most stable baryon. Baryons are particles made up of 3 quarks, and quarks are the smallest subatomic particles we know of that make up composite particles such as protons and neutrons, which are baryons because they have 3 quarks. And there are also mesons, which are particles with 1 quark and 1 antiquark, and antiquarks are the antimatter equivalents to quarks, meaning they have the opposite properties. I'm planning to make a video on antimatter soon because it was suggested and it sounds like fun. But anyway, the umbrella term for any particles made up of quarks, so baryons and mesons, is hadrons. There are also leptons, which are not made up of quarks or any other particle, and are therefore elementary. For example, electrons, neutrinos, or muons. I know that's a lot of terminology, but that's just how it seems to be with particle physics. A lot of names of things all the time. But if you want to talk to people about these things, you gotta agree on names. At least Feynman says so, you know.
Names don't constitute knowledge. Names of things. What he forgot to tell me was that knowing the names of things is useful if you want to talk to somebody else.
Anyway, Brian was talking about how the proton is the most stable baryon, and how protons were never observed to decay, and aren't expected to ever do, because things can only decay into less heavy things. Now, there are particles lighter than protons, but they're not baryons, and there's this thing called the baryon number, which is basically how many baryons there are before and after an interaction, which has to be conserved, according to the standard model. Therefore, protons can't decay because they don't have a lighter baryon to decay into, and then the baryon number before and after the decay wouldn't be conserved. And that makes sense. What didn't make sense is that a lesson or two later, we started talking about beta plus decay, which is when a proton decays into a neutron, a positron, which is the antimatter equivalent of the electron, and an electron neutrino, and how it's actually used in everyday life, like in PET scans and stuff. And I was like, wait a minute, didn't we just rule this out? What's different about proton decay and beta plus decay? The difference is that beta plus decay is not actually proton decay, because the proton is interacting with other particles in the nucleus as well. Proton decay refers to when the proton decays on its own, not necessarily within the nucleus. Beta plus decay can't happen in an isolated proton, as it requires energy because the neutron is more massive than the proton. By itself, the proton doesn't meet the required resources to upgrade to a neutron. But how does being inside the nucleus help with that? Well, the protons and neutrons in the nucleus are held there together by something, right? Otherwise, all those positively charged protons would repel each other and atoms could never be formed. You'd never exist. The reason they don't is because of something called the nuclear strong force, which binds them together and is greater than the repulsion force, and forces require energy. So beta plus decay only looks like proton decay, but it really isn't. It can only happen with the influence that comes from it being in the nucleus, so it's not true proton decay. Now, whether the proton decays or not is an unsolved question in physics. There are theories of it, but they don't follow the standard model because, well, it doesn't allow for it, as I mentioned earlier, because of the baryon conservations. So these theories go beyond the standard model and have different conservation laws. However, for now at least, despite great experimental effort, true proton decay has not been observed. The hypothetical ideas of grand unified theories, or GUTs, which are theories that try to give a single theoretical framework for the strong, weak, and electromagnetic interactions of particles, allow for baryons to change into leptons and antiquarks, and that would allow for proton decay. However, a lot of these theories are either disproven, partially disproven, or unfinished. However, there will be an experiment going on in Japan called Hyper Kamiokande, which I hope I pronounced right, if not then tell me, which is a neutrino observatory, but it will also be used to search for proton decays. It'll have a tank with 1 billion liters of ultra-pure water, and it will be buried 650 meters deep to reduce interference by cosmic radiation. It will allow for those GUTs to be tested, and provide experimental evidence for them, or help rule some of them out, because there's quite a lot of them actually. The beginning of data taking is planned for 2027 though, so that's a long time, but be on the lookout for that, in 6 years or so. But to summarize, beta plus decay is not proton decay. It can't occur in an isolated proton, as it requires the interaction with the nucleus. Proton decay can't happen according to the standard model, as the proton is the lightest baryon, and that means if it did decay into lighter particles, they wouldn't be baryons, and therefore the baryon number would not be conserved. There are theories of the proton being able to decay, but they move beyond the standard model. Okay, one person still hasn't submitted those exercises. Let me go see who it is. Crap. Thank you for the video, I hope you enjoyed, and thank you for 45 subscribers, yay!